This video illustrates the definition of a radian. First, begin with a unit circle. Now, consider an arc.
Pause. Unit circle is a circle with radius 1 centered at the origin.
Length equivalent to 1 radius. The measure of the angle subtending an arc length of 1 radius is 1 radian.
Okay, so what we're saying here is that this arc length along the circle is the same length as the radius, 1 in this case. And what we're also saying is that the angle subtended, which I've never liked that word, it just means the angle that you get from that particular arc length. The angle there is 1 radian. And it's literally called 1 radian because you're getting it from an arc length that is 1 radius long.
If we double the arc length, so that now we are viewing an arc length of 2 radii, then the new angle is 2 radians. Note the connection between arc length and subtended angle. The formula for arc length is L equal radius times angle in radians.
Okay, the formula for arc length, which is how long this is here, is the angle times the radius. So the arc length is r times theta. He said L, I guess he's saying L for the whatever, but the arc length here is just how long your radius is times whatever your angle is. So if your angle is 3 radians and your radius is 1 unit long, then your arc length is 3 units long because it's 3 radians long and each radius is 1 unit.
Another way, the angle in radians is the subtended arc length L divided by the radius. In this way, the circle need not be a unit circle. For example, if an angle subtends an arc length of 12 on a circle with radius 6, then that angle has measured 2 radians, since 12 divided by 6 is 2.
So basically he's saying there that it doesn't matter how big your circle is. What matters is the ratio between the arc length and the radius. So if your arc length is 4 radii, then your angle is 4 radians. And it doesn't matter if the radius here could be 2 units long and the arc length could be 8 units long. The arc length would be 4 radiuses worth of length, which would be an angle of 4 radians. Five radians.
As this video is wrapping up, the viewer should note that a full revolution is not perfectly divided into an integer multiple of radians. The closest we can come is 6 radians. Yet this comes short of a full revolution. Perhaps it is helpful to recall that 1 revolution is equal to 2 pi radians, which is about,
because the circumference of a circle is 2 pi times the radius.
6.283 radians.
Yeah.
Slightly above the integer 6 radians.
Sure. Okay. Hopefully you guys found that a little bit illuminating. Yeah, we don't need the next video. Although the next video, actually, I might leave this up here because, gosh, how do I not?
We start with a circle.
Okay, sorry. Anyway, sorry. I can use YouTube, believe it or not. Anyway, so hopefully that was somewhat illuminating. I'll probably post that video and the next one on Canvas because I think they are both helpful in seeing what a radian actually is. But we're going to talk about it now because, whoops, no, don't do that. I just went away from the video. Okay, cool. All right, it's back. So that's what a radian is. A radian is an angle that is not in degrees. So let's draw some pictures. So I'm going to try and, so the reason I also use that video is because my picture drawings are not great for this. Let's say we have a circle, a unit circle even, meaning a circle of radius 1. We're usually measuring angles from the positive x-axis. So right here, we would say that the angle, which we usually write as the Greek letter theta, spelled Theta if you want to spell it out. Here the angle is 0 degrees or 0 radians. Usually you actually don't write it at all, but if you're going to write it, we usually abbreviate it as rad. And then a little bit less than 60 degrees, this angle here is 1 radian, because this arc length, which we'll pretend, this arc length here is 1. Usually we use the letter S for the arc length. S is 1 radius long. So, right, if the arc length is 1 radius's worth of length, the angle it subtends, not my favorite word, but the angle it subtends is 1 radian. And then, here's what I like to think about. If you go all the way around the circle, and I know he just said this, but we're going to say it again because it's a very important concept. Kind of everything we do from now on will use some of this in some way or another. If you go all the way around, well, that length, right? That length is 2 pi radians. Radiuses, right? The length of the circle is the circumference of the circle is 2 pi times the radius. So there's exactly 2 pi radians worth of angle, right? Right, so 1 radius, 2 radiuses, 3, I should say radii, that's the correct plural for radius, radii. 4 radii, 5 radii, 6 radii, and then, like he was saying in the video, 6.28 approximately, or 1 revolution, which in degrees is 360 degrees. 1 revolution is equal to 2 pi radians. Or, as we often think of it, half a revolution, so halfway around the circle is 180 degrees. Well, halfway around the circumference is pi radii, or pi radians. So, right, and I'm gonna continue to make this distinction for a little while. Halfway around the circle, the arc length is pi radii, right? The length of 3.14 approximately radius lengths. And the angle subtended is pi radians. Right? When I write rad, I mean radians, not radii. I know they're kind of the same thing, but not exactly. Right? So from here to here, the angle is pi radians, or 180 degrees. And we are going to often use the fact that these are equal to each other. The angle 180 degrees is equal to the angle pi radians, and vice versa. Pi radians is equal to 180 degrees. So this is a very important equation. I will say typically we write it as just 180 degrees equal to pi. So if someone says the angle is a number, if they don't say the word degrees, they mean that it's in radians. So if I said the angle was 30, I would probably mean degrees, because 30 is a typical degree angle. So, but I should say degrees. So I say the angle was 30 degrees. Okay, 30 degrees is like that. If I said the angle was 30 radians, well, that's going to be a lot of revolutions, right? Because a full way around is a little more than 6. So it feels like almost 5 revolutions, right? That would be about 30 radians, because a radian is a lot bigger than a degree. 1 radian, I'll just point out that 1 radian is approximately 57 degrees. Not exactly, but it's close. So, right, 1 radian is all more than 3. A revolution goes typically, yes, Jesus. So when we'll talk about this as we go along, but when we measure angles, we measure positive angles from the positive x-axis in the counterclockwise direction. Correct.
Okay, thank you.
Well, okay, so to convert between radians and degrees, we multiply by, well, what's the only thing you're allowed to multiply by that doesn't actually change something?
1.
Right. So let me actually start this a different way. What if I wanted to convert, I don't know, 3 feet to inches? Well, I'd multiply by 1. I'd multiply by 12 inches over 1 foot, which is 1. 12 inches equals 1 foot, so that's 1. And then the feet cancel, and you get 3 times 12 inches is 36 inches. And so when you convert from one unit to another unit, you're always multiplying by 1. It's just you're multiplying by how many of that unit is equal to how many of the other units. The same sort of thing is true for changing from degrees to radians or radians to degrees. To change from degrees to radians, well, we're going to multiply by, so the thing you want to get rid of always goes on the bottom. So we're going to multiply by pi divided by 180 degrees. Right? The degrees will cancel and you'll be left with radians. To go the other direction, to change from radians back to degrees, we're going to multiply by 180 degrees divided by pi radians. We're almost never going to actually write radians or rad because we just don't. So that's how we go back and forth.
James, can I ask a quick clarifying question?
Go ahead, yeah.
So is that x times pi
That's
over 180?
just times. This
Oh, okay, okay.
is your angle. So your angle in degrees times pi over 180. And this is your angle in radians times 180 degrees over pi.
Okay, thank you.
Welcome, of course, yeah. I could use, if you prefer, I could use the dot multiplication notation. Okay, so let's convert. Convert from degrees to radians. So let's convert, say, 30 degrees. So to convert 30 degrees, we're going to multiply by pi radians over 180 degrees. And oftentimes, things are going to cancel. So I can write this 30 is 30 over 1. And 30 over 1 times pi over 180 is 30 pi over 180. And I already canceled out the units. Right? If I get degrees over degrees, they cancel out. Now you got 30 pi over 180 radians. We should reduce this fraction though. This reduces to 3 pi over 18, which reduces to pi over 6. So pi over 6 radians is equal to 30 degrees and vice versa. This is a very, so there's a few angles that are very common. This one comes up all the time. It's going to be very, very useful for you just to remember, instead of having to convert, that pi over 6 radians is equal to 30 degrees and vice versa. No, we would not. That's a good point. So wow, so if I asked, what's 30 degrees in radians, the answer is pi over 6. The answer is not approximately 0.5235. I mean, it is, but no, we never, ever, ever want to give a decimal approximation for radians with rare exception. So if someone asks you how many radians an angle is, the answer should almost always have pi in it somewhere. Occasionally not, because there's some other angles we look at sometimes, but 99 times out of 100, someone says, how many radians is that angle? Oh, it's pi over 4. It's 2 pi over 3. It's always something pi over something, usually. Let's look at a couple more. let's say I want to convert maybe 60 degrees. Well, 60 degrees is 60 degrees times pi over 180 degrees. The degrees cancel. You get 60 pi over 180, which reduces to 6 pi over 18, which reduces to pi over 3. So 60 degrees is equal to pi over 3 radians. Let's do a couple more. Let's see, do I want to say, yeah, okay. Say we had let's say we had 45 degrees. So 45 degrees is equal to 45 degrees times pi over 180, which is equal to, I mean, I feel like you can start canceling right away. Like, I don't need to write 45 pi over 180. I can say I know 45 and 180 cancel. 45 and 180 both are multiples of 9. So 45 divided by 9 is 5 times 180 divided by 9 is 20. So you get 5 times pi over 20. And then 5 and 20 reduced to 1/4. So this is going to be pi over 4. So 45 degrees is pi over 4 radians. And we can even pick larger angles, something like, I don't know, 210 degrees. If I multiply that by pi over 180 degrees, a lot of times they're going to end in 0, so we can just cancel the 0 and say, okay, well, that's going to be 21 pi over 18. 21 and 18 both are multiples of 3, so we're factoring out 3 and canceling. That's going to be 21 divided by 3 is 7 pi over 18 divided by 3 is 6. So 210 degrees is 7 pi over 6 radians. Not typically, no. You typically don't end up with decimals in either the numerator or the denominator. Basically, you should only reduce as far as you can without getting. So, I mean, you could have an answer that looked kind of silly. If I said, what's, I don't know, 7 degrees in radians, it would be 7 degrees times pi over 180 degrees. 7 and 180 have no common factors. So the answer here is not nice, but it's 7 pi over 180 radians, whatever that is. We can also go the other way. We can convert from radians to degrees. So we're going to start with radians. We're going to convert to degrees. So let's say our angle in radians was pi over 10. Okay. Well, pi over 10, we multiply by, so I'm in radians. I want to be in degrees, so degrees should be on top, radians should be on the bottom. So 180 degrees over pi radians. The pi's cancel. You get 180 degrees divided by 10, which is just 18 degrees. So pi over 10 radians, 18 degrees. We could also talk about negative angles. If you have an angle that's, say, like -3 pi over 5. So what does a negative angle mean? It means instead of going counterclockwise, you go clockwise. And I'll draw it for you in a second. In fact, let me actually draw this one. So this one here, pi over 10 radians or 18 degrees is not very big, right? So measuring from the positive x-axis, right? This is theta equals 0 radians. Maybe an angle at 18 degrees is not very much at all. Maybe it's like that. I probably overshot it. So this angle here, theta equals pi over 10 radians. Let's do -3 pi over 5. So if I multiply this by 180 degrees over pi, the pi's cancel. 180 divided by 5. So here's the easy way to divide by 5. You divide by 10 and then multiply by 2. 180 divided by 10 is 18. 18 times 2 is 36. This is equal to -3 times 36 degrees. Because 36 is 180 divided by 5. And then 3 times 36 is 90 plus 18, which is 108. This is -108 degrees. Oops, not -1080. -108 degrees. So negative 3 pi over 5 or negative 108 degrees would be, we draw it in a different color. We would start at 0, but then we would go in the clockwise direction. Maybe about to like right there. This angle would be negative 3 pi over 5 or negative 108 degrees. So negative angles go clockwise, positive angles go counterclockwise. So you definitely want to practice getting comfortable converting between degrees and radians and degrees. Oh, the ones I just erased are the kind of popular ones. Let's talk about some right angle triangles. So what we're going to do now is we're actually going to define the 6 trigonometric functions in terms of ratios of sides of triangles. So it doesn't matter how you draw the right triangle. So you can draw it like this, where this is the angle and this is the right angle, or you could draw it like this, where this is the angle and this is the right angle. Or you could draw it maybe sillily like, let's do something crazy like this. Okay. Actually, let's make it. So, in all of these triangles, in all these right triangles, there are 3 sides and they always have the same 3 names. The longest side of the right triangle, the side that's opposite the right angle, that's always called the hypotenuse. This is the hypotenuse, which we're going to abbreviate with an H. That's true here. It's true here. It's true here. Okay. The side that's opposite the angle that we're interested in. So it could be this angle or this angle. We've drawn this angle. So for this angle, this is the opposite side. For this angle, this is the opposite side. For this angle, this is the opposite side. If instead I said it was this angle, then if it was that angle, this would be the opposite side. So it really doesn't matter which of the 2 acute angles in your right triangle you are picking. For this angle, this is the opposite, which we're going to abbreviate with a capital O. So this is the opposite. This is the opposite. The third side is the adjacent. So the adjacent side is the side that the angle is next to that's not the hypotenuse. Right? Because if you pick this angle or this angle, one of the sides that's going to be next to is always the hypotenuse, and the other side that's next to that isn't the hypotenuse is called the adjacent side because it's adjacent to it. So whenever you have a right triangle and one of the acute angles, there's always a hypotenuse, an opposite, and an adjacent. And the opposite and the adjacent depend on which angle you picked. The hypotenuse is always the hypotenuse. But right, if I'm picking this angle, this is the opposite and this is the adjacent. If I'm picking this angle, then that would be the opposite and that would be the adjacent. So you actually have to pay attention to which angle you were picked when you're thinking of what the opposite and what that adjacent is. Okay, why does this matter? Well, because we're going to define the trig functions in the following way. Sine of theta is the opposite over the hypotenuse. Cosine of theta is the adjacent over the hypotenuse. And tangent of theta is equal to the opposite over the adjacent. A couple things just so I would encourage all of you to say these fully. Please do yourselves a favor and don't say sin, cos, and tan. I know it's maybe easier to say those slightly. Like tan is 1 syllable, tangent is 2, cos is 1 syllable, cosine is 2. But no one is going to like that, especially me. But your other teachers are also going to be like, what are they saying? I mean, they'll know what you're saying, but they'll be like, really, you can't say the full word. So really, you should say the way sine is spelled. So you got sine, cosine, and tangent. And I would really, really, really strongly encourage all of you to say them this way. We also have the reciprocal trig functions. So there's cosecant, which is abbreviated as CSC. And cosecant is the reciprocal of sine. It's hypotenuse over opposite. There is secant, which is abbreviated SEC of theta. It's equal to the reciprocal of cosine, which is H over A. Opposite fellows. Okay. Yeah. Okay. Yeah. And then the reciprocal of tangent theta is cotangent of theta, which is equal to adjacent over opposite. And again, just for pronunciation's sake, cosecant, when you actually write it out, it's spelled C-O-S-E-C-A-N-T, cosecant. Secant is S-E-C-A-N-T, and cotangent is C-O-T-A-N-G-E-T. So that's how you spell all those words. That's how you say all those words. There's something that just crossed my mind that I thought was important. Oh, a couple things, yeah. I mean, I don't. So if I'm thinking about how the trig functions work, I remember these three. I'm like, oh yeah, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then the other three I really remember as the reciprocals of these. So I don't really ever remember that cosecant of theta is hypotenuse over opposite. I remember that cosecant of theta is the reciprocal of sine of theta. In fact, we usually write that out. So these are some of the first trig identities that we know, called the reciprocal identities. Cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine of theta. And cotangent of theta is 1 over tangent of theta. Two things you want to know about. There is a mnemonic device to remember these first three. It goes SOHCAHTOA, right? SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. You definitely, for sure, need to memorize these trig functions. You need to memorize sine, cosine, and tangent, what they are. You need to memorize either that cosecant is hypotenuse over opposite, or preferably you should memorize that cosecant is the reciprocal of sine. So then you'd be like, oh, I know sine is this. I know cosecant is just the reciprocal with a flip of it. The other thing I want to say, and this is super important as well, is that when you're talking about a trigonometric function, sine or cosine or tangent or cosecant or secant or cotangent, you cannot have a trigonometric function without an angle that it is being evaluated at. Right? You can't say sine. I mean, you can, but it doesn't make any sense if there isn't an angle. So we don't know how to evaluate it yet, but I'll talk. Eventually, we're going to figure out like how to find what sine of 45 degrees is, or what cosine of 60 degrees is. But we can't just say like we have sine of nothing. There has to be a thing there. I always kind of relate it to, it'd be like writing the square root without anything in it. Functions have to have things they're evaluated at. They can be variables, right? You can take sine of theta or the square root of x, but you have to be plugging something into the trigonometric function or into the square root to evaluate it at. So you should never, ever be writing sine equals something. You should be writing sine of a thing equals a thing. Okay. I will try to emphasize that a lot over the next few weeks when we talk about trig all the time. Well, let's look at this next one. And I will demonstrate what I mean in this next one. I understand the desire to not write all the things because it's just time consuming. You gotta write all the things. So let's say I want to find the 6 trig functions of the following angle, theta. So let's say we have this triangle. This is kind of everyone's favorite triangle. I'm gonna draw. So notice. Oops, I gave it away. Sorry. Notice my triangle is not drawn very well. At least not the way I've labeled it. Right. It clearly looks like this side's longer and this side's shorter. Sometimes you got to deal with it. Sometimes your teachers are going to draw bad pictures, and you be like, "Shouldn't that side be 4 and that side be 3?" No, it shouldn't. I drew it dumbly. I should have drawn it like this, right? I should have drawn it more like. If I was actually trying to draw it to scale, that looks a bit more correct. But both of these triangles, even though this one's drawn like someone didn't know what they were doing, they're still getting at the same point, which is I want you to find sine, cosine, tangent, secant, cosecant, cotangent of this angle where the adjacent side's 3 and the opposite side's 4. And I know I kind of gave it away already, but we have to find the third side. And I should though, right? If you don't see that little square there, you can't assume it's a right triangle. So we need to draw that little right angle square corner thing so that we know, oh yeah, it's a right angle. So to find this third side, which we're going to pretend like we don't know for a second, we're going to use the Pythagorean theorem. So 3 squared plus 4 squared equals the hypotenuse squared. So whenever you're using the Pythagorean theorem to find the third side of the triangle, the hypotenuse squared should always be the side that's by itself. And the other 2 legs squared added together should be the ones that are together. So, opposite squared plus adjacent squared equals hypotenuse squared. And then we can find x. So 9 plus 16 is 25. So x is going to be the square root of 25, which is 5. Right? Not plus or minus, because it's a length, right? It doesn't make sense for it to be negative. Okay, now we can find all the things. And here's what I want you guys, so I'm going to show you what I mean by what you should not do. It would not be correct to say sine equals 4 over 5, right? Opposite over adjacent, opposite over hypotenuse. Cosine equals adjacent over hypotenuse. And tangent equals opposite over adjacent. What have I done wrong? I didn't write the angle. Sine of what? Tangent of what? Cosine of what? We have to write it as sine of theta, right? Because maybe, right, if I was being really obtuse about it, I could say, oh, well, maybe, did you mean this angle instead? Sine of that angle is 3 over 5, not 4 over 5. So you really have to tell me what angle you are taking sine, cosine, etc. of. And I'm probably going to be pretty strict about this because it's really important. So if I see trig functions written without angles in them, I'm probably going to knock you some points because I like you, because I want you all to get it right so that in your future classes, you're not getting knocked off points in classes that actually count for a real grade and not just pass, no pass. So please, 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 when you're writing sine or cosine or tangent, you need to write sine of theta, cosine of theta, tangent of theta, equal to whatever it's equal to. And then the other 3, we write also, and we always write them in this order, sine, cosine, tangent, and then we always write the reciprocals next to them. So the reciprocal of sine is cosecant of theta, and it's equal to the reciprocal, 5/4. This is why we write them next to each other, because then it's just easy to find the other 3. Secant of theta is equal to the reciprocal of cosine, which is 5/3. Cotangent of theta is equal to the reciprocal of tangent of theta, which is 3/4. A good rule of thumb, okay, so I think it's obvious by the naming that tangent and cotangent go together. They're reciprocals of each other. The other ones, it's not so clear. Here's what I always remember. So reciprocal functions, a reciprocal pair there's always one co-function and one non-co-function. Cosecant and sine. Cosine and secant. So there's always one co-function, one non-co-function. One co-function, one non-co-function. One co-function, one non-co-function. And they are literally named that way on purpose, right? They are literally called, right, sine and cosine, tangent and cotangent, secant and cosecant. And there is some meaning behind that we will get into at some point. Okay, what do we got time-wise? Okay, sure. So trig functions on a calculator, we're not going to spend too much time dealing with this in this class. There are some on this homework assignment. I really, really, really have to stress, if there isn't a degree symbol, it's in radians. So if someone says, you know, find sine of 30, if they didn't write degrees, you have to assume it's radians. So if I use my calculator to find sine of 30, and you are intended to use your calculator for these, I have to make sure I'm in the right mode. So if I'm in degrees, I'm going to get the wrong answer. Sine of 30 degrees is 1/2. Sine of 30 radians, so if I change the mode to radians, and I find sine of 30 radians, I end up getting negative 0.988, approximately. Actually, let's say this is an approximation. This is exact, this is approximate, just because of the nature of that particular problem. So if you're finding, for the problems where you have to use a calculator, make sure that if it doesn't say degrees, you're not using degrees, you're using radians. Another couple examples, right? So using a calculator, sine of 2 degrees, that's going to be approximately 0.0349. Whereas if I were using radians, right, sine of 2 radians is approximately, let's find out, sine of 2 is about 0.909. Let's do one more. Let's say I had cosine of pi over 5. Okay, well, that's in radians. Also, there's a pi, so it's probably in radians. So if I do it's in my notes. Cosine of pi over 5 is approximately 0.809. No one should be saying pi over 5 degrees, but if someone did, you could do that. You could do cosine of pi over 5 degrees. That would be weird though. But if you did, so going back to degrees, so change the mode. So you're gonna, for some of these homework problems, you're gonna have to change the mode on your calculator between degrees and radians back and forth. So if I did cosine of pi divided by 5, and I'm in degrees, it's going to be weird. It's going to be approximately 0.9999, which makes sense because pi over 5 is like close to 3/5. So this is like cosine of about 3/5 of a degree, which is very, very small. And I do know that cosine of 0 degrees is equal to 1. So cosine of 3/5 of a degree is really close to that. It's equal to 0.9999. Okay. Anyway, so if you're using the calculator, just be careful, right? Make sure that you're in degrees if there's a degree symbol, and if there isn't a degree symbol, even if it seems like an angle that should be in degrees, if there isn't the symbol there, you have to assume it's in radians. No worries, Paula. Sorry that your Wi-Fi was having issues. The last two things here are super, I mean, everything today is important. Like this is the basis for what we're doing the rest of the quarter. Also, it's the basis for trigonometry in general. So you will definitely, no matter what calculus series you take, you will definitely see the trig functions again. You'll have to be able to evaluate them at certain values. So these two triangles are very important. The first one I always think of as half of a square. So I'm going to take a square. of side length. I like to pick a side length of 1, but some other people like to just say it's whatever you want, meaning it's x. And I'm going to cut it in half. I'm going to cut it in half so I get a triangle. I'm going to cut it in half like this. So my triangle, one of my 2 special triangles, is what is often called the 45-45-90 triangle, because the angles are 45 degrees, 45 degrees, and 90 degrees. Or if you prefer, in radians, 90 degrees is half of 180 degrees, but 180 degrees is equal to pi radians. So 90 degrees is pi over 2 radians. And then half of 90 degrees is 45 degrees. So 45 degrees is pi over 4 radians. And the sides of this triangle are, again, I like to say they are 1, 1, and we need to find this side. So using the Pythagorean Theorem, I'm going to call this side C. I have 1 squared plus 1 squared equals C squared. So C squared equals 1 plus 1, which is 2. So C is the square root of 2. So this hypotenuse is the square root of 2. And then I do know other people will say, you could say that this is x, and this is x times the square root of 2. Basically, it doesn't matter how big the triangle is, the angles are the same, right? You could say that this was 2, 2, and 2 times the square root of 2, or 6, 6, 6 root 2, or set, right? As long as the ratios of the sides are the same, the angles will be the same. They'll be similar triangles. The other special triangle, which do I want to, how much time we got? Yeah, I might need an extra minute or 2. Sorry. The other special triangle we get by, I'm actually going to draw it on the other side and then put it over here. The other special triangle we get by taking an equilateral triangle. Which I'm going to say has side length 2, or if you prefer, 2x, and cutting it in half down the middle. Well, the angles were all 60-degree angles. So now this is still 60, this is 90, and this is half of 60, which is 30. So this is a 30, 60, 90 triangle. I also cut this side over here in half. I would like to find the height. So using the Pythagorean Theorem, 1 squared plus the height squared equals 2 squared. So the height squared equals 4 minus 1. So the height is the square root of 3. So your 30, 60, 90 triangle has sides that are 1, square root of 3, and 2. And something I remember when I do this, so when I draw a 30, 60, 90 triangle, the biggest side is opposite the biggest angle. The smallest side is opposite the smallest angle. And the medium side, which is about 1.7, is the square root of 3, is opposite the medium angle. And that's true for any triangle. The biggest side is always opposite the biggest angle. The smallest side is always opposite the smallest angle. And the medium side is always opposite the medium angle. Okay, well now here's what we're going to do. We're going to use these special triangles to evaluate the trig functions of some special angles. So if I want to find sine of 60 degrees, it's the opposite over the hypotenuse, which is the square root of 3 over 2. We do not approximate this, right? We don't get a decimal approximation of 0.8 whatever. Cosine of 60 degrees is the adjacent over the hypotenuse, which is 1 over 2. Tangent of 60 degrees is the opposite over adjacent, which is the square root of 3 over 1, which we would definitely just write as the square root of 3. Do we want to do the other 3? No, we do not. So I'm not going to write the other ones because we're close to being out of time, but I will tell you Cosecant of 60 degrees would be the reciprocal, so it'd be 2 over root 3. Secant of 60 degrees would be 2 over 1. Cotangent of 60 degrees would be 1 over root 3. We'll talk about it in a second. Let's do the 45-degree angle ones. So sine of 45 degrees. Actually, let's do it in radians. It's still the same. I'm just going to write it from. So sine of pi over 4 radians is opposite over adjacent, which is 1 over the square root of 2. Now, we usually rationalize this answer. We usually multiply by the square root of 2 over the square root of 2. And get the square root of 2 over 2. So sine of pi over 4 radians is the square root of 2 over 2. Cosine of pi over 4 radians is adjacent over hypotenuse, which is also 1 over root 2, which is root 2 over 2. Here's the thing that I always remember about the angle pi over 4 radians. Sine and cosine have the same value. Sine of pi over 4 and cosine of pi over 4 are always equal to each other. They're both the square root of 2 over 2. And then tangent of pi over 4 radians is the opposite over adjacent, which is 1 over 1, which is 1. Okay. We're definitely going to talk more about this on Monday, but I want to get this last one for you. So the last one, the last angle I want to look at is this angle, 30 degrees. 30 degrees is pi over 6 radians. 60 degrees is pi over 3 radians. So I want to find sine of pi over 6. So for this angle, the opposite is 1. The hypotenuse is still 2. Cosine of pi over 6. So for this angle, right, 30 degrees is equal to pi over 6 radians. The adjacent is the square root of 3, and the hypotenuse is still 2. And finally, for tangent of pi over 6 is the opposite over the adjacent, which is 1 over the square root of 3. We are going to rationalize that. We're going to write it as 1 over the square root of 3 times the square root of 3 over the square root of 3, which is just the square root of 3 over 3. Okay, so I know it's 11:50 right at the time. Let me say 2 things. Thing 1, these triangles are super important. You should definitely take the time this weekend to memorize them, right? You should be able to draw this triangle with the correct angles and the correct side lengths. This triangle as well. And you should be able to write it using degrees or radians. I will say the names of these are in degrees, right? No one says this is the pi over 6, pi over 3, pi over 2 triangle. They say it's the 30, 60, 90 triangle. This is the 45, 45, 90 triangle. So the names are in degrees, even though I would prefer we talk about radians. The second thing is we definitely need to start practicing evaluating these trig functions at these angles. These angles, 30 degrees or pi over 6 radians, 60 degrees or pi over 3 radians, 45 degrees or pi over 4 radians, you are for sure, without a doubt, going to be asked to find sine or cosine or tangent of these in future classes. So we need to take the time now to practice being able to evaluate them.